Thank you for coming. In true Lucas fashion, we're only 4 minutes late. So thanks for coming this morning. My name is Lucas Joppa. I'm the Chief Environmental Scientist for Microsoft. I'm also the chair of this session, so you will have to put up with me for the next bit of time here. I am pretty excited about what we have for you today because we have 3 fantastic speakers. We've got Nguyen from USC, Carla Gomez from Cornell, and Tanya Berger-Wolf from UIC, all talking about this topic, AI for Earth, which is really about applying the latest advances in artificial intelligence and academic research to the environmental sciences. It's a topic of passion for me. It's what I've concentrated my entire career on. I've had the opportunity of working as a researcher in MSR for the past 7 years until moving out into this new corporate role to direct a new program for Microsoft called AI for Earth. So this is a faculty summit session, but it's also sitting in a much broader context, which is one of the first programs that Microsoft's rolling out across the company dedicated to bringing the full power of, yes, our AI technologies, but also the 35 years of research that we've done in this space to areas of significant societal impact. Our program's really set up to focus on 4 key areas, which you can see here: agriculture, water, climate change, and biodiversity conservation. And there's 3 real pillars to the program. First is simply providing access to our technologies, so Azure grants, and those are available to academics working in this space. So we are definitely looking for proposals. Please visit our website. If you just go to Azure for Research, you will see an AI for Earth call for proposals. We would love to hear the ideas that any of you might have, or any of your colleagues who aren't fortunate enough to be here today might have to take advantage of some of our resources. We are also working on creating a bunch of training programs for bringing people on campus for multi-day in-depth trainings around some of our technologies. I know that in some cases that is a problem for academics, and in some cases it's not. But if people are interested, please let us know. And then there's also opportunities to work directly with us as teams at Microsoft, whether it's Microsoft research scientists or others across the company on these programs. So I'm not going to say much more about that. The way that we've structured today is to have each of our speakers come up. I'm going to do my level best. I know each of them, so it's probably going to fail. But I'm going to do my best to keep them to 20 minutes each. We're not going to ask questions immediately after each speaker, because I really want to be able to bring all 3 of them up here at once and allow a broader question and answer session for all of this. So we'll be hearing from Carla first, then Tanya, then Nguyen, in that order. So please, just any questions that you have during or immediately after their talks, hold for the broader Q&A session. And with that, thank you very much. And we'll bring Carla up.
Hello. It's great to be here. And thanks, Lucas, for organizing this great session. So today I'm going to give you a bit of an overview of computational sustainability, computing for a better world. And, you know, I actually now, when I give my talks, I really feel that this is, you know, a collaborative effort. So it is important to acknowledge my collaborators and also NSF that has funded this research. In fact, you know, NSF provided us with 2 expeditions in computing awards that really allowed us to, you know, nucleate this field. And this is, we have now CompSusNet, a large research network involving several universities, and in fact, Melinda is part of CompSusNet, Stefano from Stanford, and Melinda from USC, and Bistra should be also from Georgia Tech. So this is a large research network, and I want to tell you a little bit about that. Doug Fisher is also here from Vanderbilt, and am I missing So again, a large research effort. So what is computation sustainability? Basically, you know, the big picture is to harness AI and computer science to address key challenges concerning sustainable development. The notion of sustainable development was introduced back in '87 by the United Nations, a revolutionary notion at the time. And ultimately, it is the goal of sustainable development is human well-being, and therefore sustainable development encompasses balancing environmental, economic, and societal needs. And you see the 17 goals of sustainable development there. We have a variety of projects concerning computational sustainability. I will focus on you know, projects at Cornell, and these projects range from you know, balanced social economic needs, conservation and biodiversity, to accelerating discovery of new materials for solar fuel. So I hope to give you a bit of some you know, detail about these examples. Non-technical detail, so, but to give you a sense of the kinds of research that you are doing. But at the same time, I do want you to take the message that, you know, this is a very exciting area in terms of research for computer science. And in fact, I want to point out that we have a variety of projects because they really, you know, are important as computer science for us to identify cross-cutting computational themes and apply them across different domains. And, you know, we focus on big data and machine learning, constraint reasoning, automated reasoning, optimization, and citizen science. Citizen science is actually plays a key role when it comes to these kinds of efforts. So, and again, you know what, you know, as a computer science, this is exciting because this really pushes the boundaries of the state of the art, and a lot of the key questions actually, we cannot just work as we used to, you know, little areas. Now we really have to work at the intersection, for example, optimization and machine learning, etc. So, here I have another perspective of the different projects. Actually, these are projects of the CompSusNet. And what I'm trying to emphasize here is, again, that a variety of projects really have this cross-cutting computational themes. So what you see here is the lines. This is a subway line, and each line corresponds to a computational theme. And so then we have several projects along this line. And again, I will talk a little bit about these projects during my talk. And I'll start with wildlife conservation. As you know, since the Industrial Revolution, we have witnessed a dramatic reduction in biodiversity. A key cause for biodiversity reduction is habitat loss and fragmentation. And so, you know, biologists, ecologists really think that it's important to maintain landscape connectivity, to, you know, linking core biological areas to increase, allow movement between areas and increase genetic biodiversity. He is actually, there was a very nice piece back in 2006 in the science section of the New York Times talking about this project, the Yellowstone to Yukon. You know, the idea is to link these two important areas with a wildlife corridor for different species. And we actually, in collaboration with the Rocky Mountain Research Station, part of the US Forest Service, worked on designing corridors for grizzly bears and other species, and just for you to see how this is actually a simple, I mean, how it translates into a computational question. You want to connect these three reserves, Yellowstone, Salmo Salway, and Glacial Park, and you can represent, you know, this, the different parcels with nodes, and then in this graph you have, so the nodes correspond to parcels, and there's an edge if a bear can go from one parcel to the other. And now you have the reserve, so your goal is to connect this and form a corridor. If you just want the minimal cost solution, this is a well-known problem in computer science, the Steiner tree problem. And basically, in fact, I'm just reminding you, this is what exactly when we are setting up a connection for a video conference, we are solving, you know, the computers behind the scenes, a Steiner tree problem. So that means that, you know, we can actually leverage tremendous advancements from network design to study these problems, in particular, for example, for landscape connectivity. But, you know, what's also interesting is that, you know, these problems pose new challenges. For example, we need to factor in different species, different requirements, and they lead to new methodologies that we can then, you know, generalize for other applications. So this two-way street is really makes it exciting also for computer scientists. And using, you know, a variety of techniques, we actually can produce optimal or near optimal corridor designs. And for example, we show that a minimal cost corridor for the grizzly bears would be around 8 million, which is less than an NSF expedition. So if you have more money, you can actually do better. And, you know, we worked on generalizing this for other species, and actually we have a very interesting collaboration with Ecuador, actually involving several researchers, and the idea is to build the socio-ecological corridors for the Andean bear, which is an umbrella species in Ecuador and South America, and by you know, designing corridors for this species, we automatically consider many other species. This is a more challenging problem because now you really need to also consider, you know, the social implications and support the local communities. Actually, Bistra is also part of this project. I thought I would now talk briefly another project concerning evaluating the impacts of dam proliferation in the Amazon basin. This is actually Alex Flecker is an ecologist, he's actually right here, and he's putting together this, you know, amazing team of ecologists, biologists, sediment specialists, hydrologists, etc. And so here, and just to give you an idea, for in the next 10 or 15 years, they have planned, or they have under construction of plans for more than 500 dams in the Amazon. So that will have tremendous implications in terms of ecosystem services and in terms of, obviously, energy, but also it may affect negatively transportation, connectivity, fisheries, etc. So just so we are working on this problem, and as you imagine, you know, different configurations will have different impact in terms of ecosystem service. And here I show how, for example, in terms of connectivity, this one really is worse than this one. And for example, we are looking at the trade-offs. Here you see we study the trade-off in terms of energy and connectivity for the Western Amazon. And in scenario A, you get much energy. So this is the energy axis and connectivity. And so we get a lot of connectivity. And that's what we show here. Now, if you increase energy, now you see you remove big chunks of the network, so the connectivity starts going down. And in case C, now you have high levels of energy, and really the connectivity goes down dramatically. So we are working on, here we are also working on the criticality of, understanding criticality of dams. For example, the solution on the left is much worse than the one on the right, because it really, blocks main stems of the rivers, and the output of some of these dams actually is not very high. So we are extending this work for the Amazon and for a variety of ecosystem service. For example, now we can generate the Pareto frontier for this that involves about 9,000 solutions. So we are looking at these different options. So how do we relate our models to data, to the real world? We basically need data, and we use data from all kinds of sensors, remote sensing, the land satellite, etc. And we also use an amazing sensor that's the best sensor. So no doubt this is the best sensor, for example, for recognizing species. And in fact, the Lab of Ornithology at Cornell has this great program, eBird. It's a citizen science program that, with over 300,000 volunteer birders that have submitted over 300 million bird observations that correspond to over 22 million hours of field work. 3 times, that's 2,500 years of field work, more than 3 times the labor that went into the building the Empire State Building. So combining those data with environmental data and using computational resources such as the Microsoft Azure, we can relate the environmental predictors to the patterns of occurrence and absence of species using machine learning models. And that's what you see here. This is actually the output of a machine learning model. And so now we know, we can identify bird migrations, and these models also reveal the habitat preference of the birds at a very fine resolution, which allows us to have new novel models for conservation. And there's a great example is this, the Nature Conservancy has this program called Bird Returns to protect migratory water birds in California against the drought. And basically this is a combinatorial reverse auction where farmers submit bids to keep water in the rice fields coinciding with the bird migration. So that is only possible because of these very fine resolution eBird models. Using this program, they have created substantial additional habitat for the water birds, and this is really only possible because of these now very powerful computational models with a very fine resolution in terms of habitat preference, etc. Just let me mention that we have a similar citizen science program in Africa to get, detailed forage maps for Africa. Contrarily to the US, Africa is very poorly sensed. And I also wanted to mention a project, Stefano Ehrman is leading this project on using satellite imagery and machine learning to predict poverty. There are some issues, and you know, one of them is, you know, citizen science is great, but you know, there are limitations. For example, because they are volunteers, we can't really tell them go here or there. So bias, you know, data bias is a real problem. So we are developing games to really, based on this principal agent model, to really incentivize birders to go to the places where we need data. And this, again, from a computation point of view, this is a very interesting problem. And basically, you know, this is, you may have heard of Pokemon Go. Well, this is the real version of Pokemon Go, where we give points to birders, they collect, and at the end of the season, there's a lottery where they gain binoculars proportional to the number of, so the chance of getting the binoculars is proportional to the points they collect. And, you know, we were amazed to see e-birders are ideal. Or birders are really the best citizen science you can think of, because they actually are so fanatic and dedicated. And we saw that with this avicaching game, we could really move them to undersampled areas. I have I'm trying to really stay, I have 5 minutes. I thought I would now mention a very different area that we are also very excited about, and that concerns using, you know, AI and computational techniques to accelerate materials discovery for solar fuels. You know, Obama in 2010 created the Materials Genome Initiative to accelerate and incentivize the pace of discovery. We are working with the Joint Center for Artificial Photosynthesis on solar fuel cells. The cool part about solar fuels is that they can be stored and used later, as opposed to just, you know, solar panels. So this is a very exciting area for computer science, and basically just to give you an idea how this works, you know, they have these high throughput experiments where they have like an apparatus like 3 guns, where they with, like, say, 3 metals, like atomic spray painting, they mix up materials so they can rapidly synthesize thousands of materials, and then they can use the synchrotron to rapidly characterize thousands of materials. So the bottleneck is really about you know, inferring the crystal structures from the X-ray diffraction data. And you know, this is, you see here, you have, you know, a bunch of samples, X-rays. These are like the spectrograms all stacked. And what you want to do is to infer from this the crystal structure. So this is a data interpretation problem. Why is it so exciting? Because, you know, for us, you know, this defies the current state of the art of machine learning, because we have to produce results that obey physical laws. And so hard constraints that are difficult to enforce. And this is essentially currently a manual task. Just for you to see that, yes, this problem is very specific, but actually this problem is it's a source separation problem. You are given a signal. You want to, in this case, from the signal, identify different crystal structures. We are working on other problems. They may look very different. For example, monitoring elephants in Africa, where we have audio signal, and there we want to separate the elephant calls from the bird calls, from the gunshots, etc. So from a computation point of view, these problems are actually very similar, and you probably are familiar with another source separation or problem problem that is topic modeling that is, like used for in a variety of settings. So we developed, an AI platform using, exciting algorithms in machine learning and matrix factorization, and that led actually to the discovery of a new platinum-free catalyst, and that is very exciting. And actually, more recently, our collaborators, again, using this system that we deployed at, again, the Joint Center of Artificial Photosynthesis at Cornell and SLAC at Stanford, they discovered a new family of solar light absorbers. So our big picture for this example is actually to use AI and other techniques to build a Sarah, a female robot that is going to, can you show me that? Wrap up, I will. So Sarah is actually, stands for Scientific Autonomous Reasoning Multi-Agent that is, will encapsulate the full scientific discovery cycle from formulating hypotheses, devising and planning experiments, and analyzing results, and combining all kinds of informations like, a very scientific Q&A system, including, quantum mechanics, etc. So, again, this is a very exciting research area. Even though we have these different applications, we have these underlying cross-cutting themes from computational themes. And for example, I talked about, the materials discovery. That was the last topic. But, this problem also is similar when it comes to elephant coal detection and electricity usage disaggregation. So there are many problems that fall into the same framework. So to wrap up, this is a very exciting area. On one hand, we think we can inject computational thinking to address sustainability questions, but this is really a two-way street. We are, by studying these sustainability problems, we are exposed to new challenging problems, and also new formalisms and concepts that we get from other disciplines, often very powerful, but they are not powerful from a computational point of view. That's where we come in and provide our expertise. And obviously, the big reward is that we are doing, we hope to have societal impact. Thank you so much. And again, I would like to thank my collaborators, because this is really, it takes a village. Thank you.
So how fast does the population of elephants in Africa decline? Where do the whales go? How many turtle hatchlings survive to adulthood? How many snow leopards are left in the world? It's a basic question, the answer to which we actually do not know. IUCN REDLIST, the International Unit on Conservation of Nature, which is the official body that determines the conservation status, has this to say about snow leopard population. Many of the estimates are acknowledged to be rough and out of date. The best we have is about 15 years ago. Snow leopards, the iconic species. Elephants, the effort was to get a very rough estimate of the savanna elephants took $2 million and 2 years, and it's not scalable or repeatable. Scientists cannot track all animals at all times everywhere. We can put GPS collars or radio collars, but those are actually take a lot of effort, cost thousands of dollars per animal to put one on, and can be dangerous to the animals themselves, unfortunately. So what do we do? Today, images are the most abundant readily available source of information about animals, about wildlife, or actually about many, many other things as well. So they come from camera traps, field assistants, tourists, such as safari goers or whale watchers, park visitors, accidental photographers, and Instagram, Flickr, and everything else, if we can only actually get the information extracted from those images on the animals, right? So we try. So we built a system that can do just that can take thousands of images from any source and get the information on who is the animal, where it is, and when is the image taken. And then from all kinds of sources, with all kinds of citizen science input into the system at every stage, from the data collection to tagging and annotation, but also the education at the end. But the system then can also be queried for all the information for scientists and conservation managers. So here's how it works. So can you find all the elephants or zebras in these images? Come on. So we can pull out all the images containing different species and pinpoint not only that this is zebra giraffe, but also where exactly the animal is. So that's not a big shocking revelation that it's done using deep convolutional neural nets. We pull out more than the location of the animal, the localization of the animal in the image. We also, the position, which is different for different animals, the viewpoint, the quality of the image, and so on. And then, not only we tell you that this is a zebra, but we can ask which particular zebra is it of all the zebras out there. So this is Zippy the zebra, and Willy the whale, and Terry the turtle. And we can do it for anything striped, spotted, wrinkled, notched, or uniquely identifiable animal. I'm wrinkled. A uniquely identifiable animal, or flukes, or fins. And so together, that's the research paper that gave rise to all of this. And so together with the information on when and where the images were taken, we now actually can track an animal over time. We can count. So this is an example of the system, Wildbook, for several species of cetaceans, humpback whales, sperm whales, and dolphins, bottleneck dolphins. We call it Fluke Book because we use the shape and the color were available for the patterns on the flukes of the whales or the dorsal fins of the dolphins for identification. And so this is the celebrity, the most cited in the entire Fluke Book, which now, it started out with about 800 individuals. Now it has more than 11,000 identified individuals about 2 years later. And this is the celebrity whale, Pinchy. So she's been cited more than 520 times. This is all her social network, who she's been cited with, and then there is the other biological samples. She also has a calf, we know that, and then, but she hangs out, all 500 sightings are around this tiny island in the Caribbean, Dominica. So she doesn't go far. But with this information, we can now really do population counts and birth-death dynamics and species range and social interaction and interspecies interaction, as well as the interactions with the habitat when the information is available. So not only that, but so this is an example of another wild book. This is for whale sharks. You can adopt an animal, so people now started adopting an animal. You can see who else has seen this animal, and you can form collaborations of these researchers and citizen scientists who've cited the same animal. We now scrape YouTube images daily to identify. So we pull out the frames that contain whale sharks and then use natural language processing to get the location of the video from the speech around or from the audio of the video itself. So I looked at whale shark yesterday, and I was showing it to a few people. And from yesterday to today, overnight scraping added 3 sharks to the database. So this system started with about 200 individuals. It's a volunteer effort by divers and people interested in whale sharks. 200 individuals 15 years ago. The initial database didn't have computer vision until recently. And today, it's more than 8,000. So the latest number, just looked up, 8,441 individuals. So this is when I put the talk together a couple of days ago. So now it's 8,441 with almost 40,000 sightings, more than 5,000 citizen scientists participating. Okay? So that's scale. It allows us now not only to create a database, but this wild book for whale sharks is the basis for the official number of the global population size estimate by IUCN Red List. Okay. The first deployment of wild book was at the Lewa Conservancy in Kenya. It's the only UNESCO World Heritage Site in Kenya in January 2015. That's the duct tape version when we just kind of threw everything together. And it was used, so this is a server that is standalone server at Lewa. Thank you, Microsoft. There's a long story of how it actually got to Kenya. There's even a footage of it somewhere. But it's used there to monitor the gravy zebras, which is the endangered species of zebras. And they normally do a monthly patrol. So this is the headquarters also of the Gravy Zebra Concentration Trust. They do monthly patrols where they take pictures of the animals. They have Palm Pilot with all the information that they enter. And they have a separate GPS device. And then they come back and use an Excel sheet to upload all that information and by sight identify the individual animals from the photographs. That's until we deployed the system. Also, until we deployed the system, they had a sense that there are not enough juveniles surviving to adulthood in the population, even though the numbers overall seemed okay. But, if the numbers of juveniles, are not, if not fewer than the adults, then what's happening? The population is declining, right? And so why do we think that there are not enough juveniles surviving to adulthood in a preserve, in a nature conservancy where nobody's shooting them? Well, lions. They're doing also a great job on lion conservation. So there are too many lions. So after the system deployment, and it has been running for several months, they actually had hard numbers, evidence, that indeed there are not enough juveniles surviving to adulthood. And with these numbers now, they could go to the Kenya Wildlife Service and start a population management program for lions. Don't get scared, it's contraception. So last January, in 2016, we did the first ever full census of an entire species using people driving around taking pictures. So this is the same gravy zebra. 98% of whom are, 95% of the species are in Kenya. There are a few hundred in Ethiopia. And for 2 days, hundreds of people all over the country, from local tribal chiefs and kids we had donations of GPS-enabled cameras to tourists with telephoto lenses, and US Ambassador to Kenya, Bob Kodak, drove around, took 80,000 images, 40,000 of them actually contained zebras. We identified each animal and got the most accurate count of the species ever in history. This is the number now officially that IUCN Red List uses. So we've done and verified not only that the saturation, the sighting of new animals over the 2 days flattened out. Essentially, we've got every single animal out there. The compliance rate among all these hundreds of people with minimum instruction was very high. We could use about half of the images that they took, which is high. They covered the area that we asked them to cover, going to the northernmost borders of Kenya, to the So this is the Grevy's zebra, sorry, the line separating. So this is the line separating the two maps, the two events, to the southernmost reaches. They covered the country. They had good coverage, and which resulted in the most accurate count because of that. So this is a graduate student who led the whole data analysis and supported the whole system, Jason Parm from Rensselaer Polytechnic Institute. So as I said, now this is the official number for the IUCN Red List population count. Yeah. So we started already not only from taking data, not only from scientists and field assistants and tourists and citizen scientists, but we can start going to an online platform for citizen science and Instagram and Flickr and Bing and Google and YouTube, as we already saw for whale sharks. But if we are going to take this data from Flickr, how biased our estimates are going to be? That's the question that we were concerned with, and the collaboration with Microsoft Research, Lucas and Emre Kitcheman, on estimating the bias of social media. So we start with the true population. There is a spatial-temporal bias of actually being able to see an animal when you're there, so being at the right time at the right place. But that's the bias that's known regardless of photographs, right? The next thing is what people, given that they're seeing all these animals, there is a bias in what people are going to photograph. We've taken pictures from the same car, tour car, going on a safari, and some photograph only birds and take 500 pictures of those, and others will take 12 pictures of, you know, a beautiful elephant, one rhino, that's it. So as though they have been completely different tours. The next part of bias is what they're going, given what pictures that they took, what they're actually going to put on social media, and on which social media, right? And then how do we collect that data? Do we take only publicly available images? What kind of search terms are we entering? How do we scrape it? And then how do we estimate? Which model from that do we use to estimate the actual population? But what really, really matters is not figuring out exactly all these biases, but the match between the true population and the population estimate, right? That's our error, not the combined, which represents the combined error, but we don't need to know exactly each one of those. And so we've done, one of my just graduated student, master student, Sridhar Menon, in collaboration with Microsoft, we've done an Amazon Mechanical Turk study of asking people, given these sets of pictures that people took on the Grevy zebra rally, the Great Grevy's rally, the count of Grevy zebras, to select which ones they would post. I mean, it's obvious which one they would choose to post on social media from these ones, right? It's these ones. No. All right. Then, so we asked for each picture, would you post it? Would you post it? So the amazing thing is the results, yes, there is a lot of bias, and it's very clear which pictures make it to the social media or not. But the eventual counts are not biased to species, to age of the animals, to the viewpoint, to the identity of individual. The time of the day is the night ones are not making it. So that was the amazing result, that from all of this, it actually doesn't matter with respect to the question that we're interested in. We can estimate the actual, so this is the baseline, we can actually reasonably accurate estimate the population size resulting from all of these biases, right? It's a learnable problem. And there seems to be evidence that there is no actual animal bias towards any specific animal from all of this. So much so that we scraped Flickr public images for Grevy zebras and decided to compare them to the simplest population estimate from those, to the population estimate that we had from the Great Grevy's Rally, from the massive citizen science effort. So we remember we're comparing it against January 2016. So the only thing that matters is really this estimate, right? So we're comparing it against January 2016, and here's the error. Less than 1% error by taking pictures from Flickr, public images. We can get an estimate. Okay, so we don't know if it only works for Grevy zebras, if it only works for this particular year, so we're continuing this study. But this in and of itself shocks shocked all of us. So we now have built about a dozen of these wild books for different species. So as I showed you, a wild book for whale sharks, wild book for cetaceous, fluke book. In collaboration with World Wildlife Fund, we have now several projects. This one is for the salmon-ringed seals in Finland. They had estimated 298 are left in the world. They're highly endangered. We now have 305 in our wild book. So clearly, they're more than they thought. One of the project collaborations, so with WWF, we also have project wild book for lynx, for Iberian lynx, and my favorite, Internet of Turtles, IoT, the real one. All right. So machine learning and data science in a smart way allowed us to take this data scarce but critical, data critical discipline, of studying wildlife and conservation, and allowed us to go from images, from pixels, to science conservation and policy and public engagement at a scale and resolution never seen before over space and time and individual animals. Right? And clearly this is a joint effort of many, many, many people. So this is the wild book is the 4 co-founders from, so let me pull them out. Dan Rubinstein is an ecologist from Princeton University. Chuck Stewart is computer vision scientist from Rensselaer Polytechnic Institute. And photoshopped here is Jason Holmberg, data architect from wildme.org. And Lucas it's a different trip, so we'll Photoshop you separately. Lucas has been to Kenya. This has been taken in Kenya, and so but there is Lucas and Emery, with support from many wonderful organizations, including Microsoft Research. Thank you very much.
Hello?
Yeah.
Okay. Thank you, Lucas, for organizing this wonderful session, and thank you, Carla and Tanya, for your great talk. So I'm going to be talking about in AI for Earth on AI for protecting wildlife, forests, and fish. So the work I'm going to talk about has been conducted at the USC Center for AI in Society. This is a collaboration between our School of Engineering and School of Social Work. I'm a co-director of the center from the AI side, and Eric Rice is a co-director from the social work side. Our mission is to advance AI research using the grand challenges, the 13 grand challenges of the American Academy of Social Work and Social Welfare. I've listed just a few, and these are big things like ending homelessness, achieving equal opportunity and justice, and great things. And the international version of this is, of course, the UN Sustainable Development Agenda that Carla brought out. Now, clearly, these are grand challenges. What can we practically really do? So I'm going to highlight 3 areas of work at our center. The first, borrowing from Lucas's AI for Earth, is indeed a focus on AI for Earth. One concrete project that I'll focus on in my talk today is work we are doing with Wildlife Conservation Society and Uganda Wildlife Authority in trying to protect endangered species in Uganda. And the challenge here is these snares that get placed. So if we can, using machine learning, predict where snares are placed and get them removed before they kill animals, we can save wildlife, and we can generate patrols to get these snares removed. I'll show results where we've done this work and over several months now allowed snares to be removed, potentially saving lives of animals and poachers to get arrested. In this area also is work we're doing with another NGO in drone patrols in South Africa and detecting poachers and animals in the infrared video
and then we can send rangers to try to interdict the poachers. I may not get time to talk about this, and I'm certainly not going to get time to talk about some of the other projects that we've done, working with the US Coast Guard to generate patrols in the Gulf of Mexico against illegal fishing, and work with an NGO in Madagascar to try to prevent illegal logging. Now, this work builds upon our prior work on AI for public safety and security, which is also another area of work at our center. The challenge here is that we have a large number of targets to protect, but limited security resources. How do you then schedule or plan or allocate limited resources? We appeal to game theory, and by solving massive scale games, we can generate patrols, for example, for the US Coast Guard in different ports like Los Angeles, Boston, New York, assign air marshals to flights, and work with other agencies in the Los Angeles area. So I'll briefly touch upon this, as this is background for some of the work. We are excited that several researchers around the world are picking this up. For example, Professor Sarit Kraus in Israel is using this to do traffic monitoring. Other collaborators in Singapore to generate patrols in Singapore, and for drug interdiction and so forth. A third area of work that I'll not get to talk about today morning, but please come to my talk today afternoon if you are interested, is AI for low-resource communities. This is work that we are doing with, for example, a concrete project here is working with the homeless shelters in LA. A challenge is, how do you spread information about HIV amongst homeless youth? Harnessing the social network of these youth, we are able to show that AI algorithms can spread information far more widely compared to the traditional methods. We've done pilot tests in homeless shelters and shown that this is more effective. AI algorithms are more effective in spreading information. But it's not only spreading information. A concrete result are these smiling youth. So sometimes AI programs provide a bias in a very positive way, and I'll talk more about it later today. The other projects in this space are AI for intervening in substance abuse and in suicide prevention. These are all ongoing projects. Now, all of this work is only possible because of partnerships with different organizations in the space of wildlife conservation. It's a partnership with WWF, WCS, and other NGOs. In public safety and security, it's with the US Coast Guard and TSA and other law enforcement agencies in LA. And for low-resource communities, it's with homeless shelters like Safe Place for Youth and My Friend's Place. As I said today morning, I'm only going to be focusing on wildlife conservation and briefly touch on our work on public safety and security. Now, people are very well aware of the tremendous loss in elephants and rhinos and so forth. To understand the situation firsthand, I went to Murchison Falls National Park in Uganda. There's wonderful wildlife there, but there's threats to the wildlife. Snares, thousands of them used to trap animals. So in order to combat that, we've been building this system called PAWS, Protection Assistant for Wildlife Security. The challenge for PAWS is that we have massive forest areas, thousands of square miles, and limited security resources. How can we generate intelligently randomized patrols in these forests? And these need to be based on learning adversary models. So to understand more of these patrolling problems, we've been to different areas. For example, this is a patrol boat in Bangladesh for the Global Tiger Conference that we were at. This is a conference, the only conference I've been where we got police protection as we walked out of the conference. Hasn't happened at AAA Rich Guy. It's another trip we went on, patrol with rangers in Indonesia. So one of the side effects of this work is our ability to go to all these wonderful places and understand the challenge that they face. On the top right-hand corner there is Fei Fang, whose PhD work this part of this talk is borrowed from. I'll highlight the role of the lead PhD student in the talks in the top right-hand corner. So let's start with generating intelligently randomized patrols. As I said, this work builds on our prior work on AI for public safety and security. And for the benefit of those who may not be aware, I'm going to give a 2 to 3 minute introduction to this work, which is conducted over 10 years. And so this work started in 2007 with LAX police, the airport police, saying, how to allocate checkpoints roads. There's 8 inbound roads at the airport, not enough officers, 8 terminals, not enough dogs. How can you schedule or plan or allocate these security resources? So we've been using game theoretic approaches now. This is, of course, rock, paper, scissors. And the outcome is determined by who wins and who loses. And if you are advising player A, you would say, randomize over rock, paper, and scissors. And that's the basic insight that we use in solving these games. When we talk about games between the police and an adversary, the game is much more complicated. There's a lot more strategies. The payoffs are much more complicated. But it's still a game, and we're solving it to generate randomized strategies. The kind of games we solve are called Stackelberg security games. They're security games in the sense that they're played over targets. The payoffs are based on whether targets are covered or not. These are Stackelberg games because the defender acts first. They generate randomized patrols. The adversary can observe that and then react. So the main challenge, of course, is to solve these massive scale games. And by solving these games, for example, when they were deployed at the airport, sometimes they lead to arrests of people carrying large number of weapons into the airport. I was very happy 10 years on now. 2 weeks ago, we had a conference at USC, and the police chief was saying, we use game theory. So I was very happy to see that people. And so on. This has now gone on with the Federal Air Marshal Service. So if you've been on a US air carrier on an international flight, whether there was an air marshal or not, is a problem that's solved using these games. For port patrols in different ports like New York and LA and Boston, that's also solved. Or patrols around the Staten Island ferry. This is our algorithms at work. This has completely and radically changed how the Coast Guard used to do these patrols. And the threat they are trying to screen against is somebody trying to ram a suicide boat into the ferry. So this work has gone on and been deployed by many different security agencies around the world. And as I said, with our colleagues and collaborators now, we're very happy to see it being used in many other countries. Just to sort of, and this is lead to, this is more effective. We can show it in different controlled experiments. This is numbers of ticketless travelers caught in LA's trains, first using game theory versus previous methods, and showing that the game theoretic approaches can be more impactful. An uncontrolled experiment here, before to after, in terms of before armor was deployed at LAX to after, the number of arrests have gone up. Okay, so this is all previous work. How do we apply it for protecting wildlife? So we're going to take the park area and divide it up into grid cells, 1 kilometer by 1 kilometer. Each grid cell is a target. Now we can play a security game where if there's a water body, now we know that that has a higher value target because there's more animals there. Now we're going to solve this game, generate randomized patrols. When the adversaries attack, poachers attack targets, we get data. And from that crime data, we learn an adversary model, and that improves our patrols. Let's focus on the game theory portion of this. This can be solved as a security game. We did it. We generated patrols. We handed them over to our collaborators in Uganda. Andrew Lemieux tried them out. Panthera tried it out in Malaysia in the Taman Negara forest area. There's a poacher's camp that was found. But the feedback that kept giving us is that we aren't paying attention to geography. So we were in LA, they're in Malaysia, we're having these Skype calls, and they're telling us that the shortest distance between 2 points is not a straight line. And this didn't make sense. So we flew down to Malaysia ourselves. So this is us, beginning a patrol in the forest in Malaysia. This Boan, a former postdoc, this Faye, she's here, and me, and we started, we're very happy. We get to patrol in Malaysia in a forest, hacking through the forest, finding a poacher's camp, exhausted at the end, and the guide is telling us you still have to walk 1 kilometer. But we understood something important. The shortest distance between 2 points is not a straight line in a forest. You have to walk along ridge lines. You have to walk along riverbeds. And these constraints, so there's a hidden street map that needs to be taken into account. This is what's done in PAWS that leads to better patrols, and we can now show that this was a preliminary evaluation, that we can see more human signs with PAWS patrols compared to previous patrols. But this is generating patrols. Now let's look at the other side of the equation, learning adversary models, so we can generate more impactful patrols. And so this is part of a PhD work of my former student, Nguyen. And so her task was to figure out, given this set of grid squares, where would an adversary attack? And so we have past crime data from the Queen Elizabeth National Park, 12 years of data, and we're trying to predict, based on the different features that we have been given, how likely is an attack going to take place on a grid square. So we have range of patrol frequency, animal density, distance to roads and rivers, area slope, et cetera, et cetera. So the first attempt was to build a dynamic Bayes net. It's a two-layered model, attack probability and detection probability, because when a ranger goes to a location, they may not actually find an attack. And so we want to predict these probabilities using all these features. We did this. Unfortunately, it seemed like there's just not enough data over the entire park. And so we needed somehow to figure out how to, how to get around this problem. So we ran a hackathon within our group to figure out who might come up with a better model. And the model that seemed to win was an ensemble of decision trees with feature boosting. And this, basically, you do a majority vote and say, this is the area where, this is the 1 kilometer by 1 kilometer grid square where an attack is going to take place. This prediction can be improved in localized places where there is more patrolling, going back to this earlier dynamic Bayes net model, which is more data hungry. And so using all of this, we ran simulations. So this is looking at, given past data from previous years, can we predict attacks in 2015? And so on the y-axis is LNL score, a metric of accuracy. And you can see that the best model we have was significantly more better performing than other models that we had, other standard machine learning models we could throw at this problem. But this is data from 2015. What would happen in 2016? So here, we first did a 1-month pilot test. We chose 2 9-square-kilometer areas. These were deliberately chosen to be areas where there were infrequent patrols, there were no previous attacks, and we are trying to see, we're sort of saying, you haven't patrolled these areas, we predict you will find attacks in these areas. And to make it more interesting, this was done 1 month before the AMAS deadline. If you find attacks, there's a paper. If there's no attacks, there's no paper. And so this is the way we found these places. And look at this, these green spots you can see, they don't overlap with the red. The red are the previously cited seen attacks. And this is, again, the reds are far away from the green. So we are asking them to patrol completely new areas and say, here's where you're going to find snares. Okay, and so the rangers get the data, and this is how the patrolling proceeds. They'll walk out, and in this case, we're lucky they found a snare, and now they'll record it, and we get to know there's a snare used to kill animals. So we started, 2 9-square-kilometer areas. First email started coming in from Uganda. Okay, there's 19 signs of litter and so forth. Well, it doesn't quite help us. It's good to know. 1 active snare, that's good. And then a poached elephant. So that's sad, but it tells us that we are in the right spot. We are in the right place. The poachers are active in this area, but in this case, we are too late. But then 1 whole elephant snare roll. So poachers were active in this area. They were killing elephants, but before they could kill the next batch of elephants, a snare roll that was hidden away was removed. And obviously, hopefully, this means that we saved some animals. And then 10 more antelope snares and so on. I should point out that I'd also given the students a reward. Every snare found would be a drink, a free drink on me. At the end of up to this, they were okay. Then they said, okay, no more drinking here. So this is our hit rate compared to the historical hit rate is higher. Our hit rate is higher. And so this is a good pilot test. An AMAS paper got done. But let's raise the stakes and say, run a larger scale test, 6 months, and this is for a thesis. So if you succeed, your thesis gets completed. And so here, there's 27 areas, 9 square kilometers each. We divided them up. Some, we said, were high areas where you will find more snares. Some low areas where you will not find many snares. 5 areas were high, 22 areas were low, according to the proportion of high and low in this park. And there's a lot of constraints on where the areas could be. They had to be a certain distance away from patrol posts, all of that. And the rangers were trained to use the software to go out and find these locations. They were unaware of this classification. They were not told which were high and which were low. And they went out, and we measure effort in terms of catch per unit effort. For every kilometer walked, how many snares were found? The rangers walked hundreds and hundreds of kilometers trying to look for snares. And the question is, what would really happen? And so fortunately, our high where we predicted the capture would be high. The catch per unit effort was 0.11, where we said there would be fewer snares. Catch per unit effort is 0.01, a 10-fold difference. And so clearly we are doing a good job predicting where snares would be located. And in fact, the historical catch per unit effort is 0.04. So the rangers, when they are walking by themselves without the use of our software, their hit rate is much lower. And so based on this, we're very happy the thesis got completed, et cetera. But there's very interesting side effects. So as the rangers were following going out to do this experiment, one day they said, well, we found a poacher's trail. They followed the trail, found a camp, ambushed a camp, arrested poachers, confiscated wire snares and cooking pots and all sorts of things. We can't report this as part of the experiment because it's outside our area, but a good side effect. Other areas, they've chased poachers. I wish we had a video of that in one of the areas. Other kinds of things that were found. So the goal here now, given that this seems to be working, is to really test it more extensively in other parks, Murchison Falls National Park with the WCS in Cambodia and with WWF, and hopefully include this in the smart software so that it can be deployed worldwide in predicting poaching. I wanted to close here in the last few minutes by talking about another project. It's patrolling from the sky. This is work with the Air Shepherd, an NGO. Worked on my PhD student, Liz Bondi. And so the drone flies. The idea is that if we can, in real time, figure out where the poachers are, where the animals are, then we can call in the rangers and try to interdict poaching. So this is nighttime. We get the real-time video. And this is 3 poachers hiding that were found and so forth. So I'll end here by saying that there's a whole lot more that can be discussed, but running out of time, so let me talk about the main points. There's significant potential for AI to contribute in this effort, and congratulate Lucas for starting this effort on AI for Earth. But these are not just applications of existing technology. There are fundamental computational challenges, AI challenges, from this user-inspired research. But as we design these algorithms, as we design this newer kind of AI, there are clearly challenges of understandability, transparency, interpretability, and in complementing human autonomy. Briefly, by interpretability, I mean, when we say, okay, you have to go there, and when we first were telling the rangers to go to a certain location, you're going to find snares there. The question is why? And if it's a very complicated model and we can't quite explain, they're not going to go. It's a lot of effort. They're going to walk hundreds of kilometers. It doesn't work like that. Complementing human autonomy, you got to find the right balance. We know there is, say, a 1 kilometer by 1 kilometer grid square where snares may be found. But we won't be able to tell the rangers, okay, they're going to be hidden under this particular bush. That's the kind of expertise that they have. And so figuring out the right balance has to be important. I'll end by saying that there's also a methodological challenge here, in that this is kind of work which gets done not in the lab, but in the field. And we are collecting data from the field. And this is not work where necessarily proving theorems and algorithms. Beyond that, it's the next stage where we're collecting data. And there needs to be a way for us to encourage this kind of work, to be able to publish this kind of work. And this is a very, a new place for doing this kind of interdisciplinary work. Today, unfortunately, this is likely not going to get accepted at our conferences. So this is something we need to pay attention to in order to foster this new kind of science. So I'll end here by saying that there's a tremendous opportunity for AI for social good. And if you're interested, please come to our website, case.usc.edu. Thank you.
Well, thank you guys so much. That was, I know all of this work, and every time I hear it, I get more ideas for what we need to do next. Carla's getting some water, but we're going to have all 3 presenters come up here. We have 15 minutes, I believe. Is that correct? Yeah, we have 15 minutes. First of all, I just want to thank the presenters for actually doing the almost always unachievable, which is sticking to our time. So I will be up here as well. You can ask me questions, but you should ask the presenters questions primarily. And we'll kind of go in a first come, first served sort of way with questions. So that was impressive. So yeah, let's go. And I believe there will be a microphone walking around from person to person. So.
Kishore Ramachandran from Georgia Tech. All three talks are fascinating. Being a systems guy, this is completely new for me, so I was really blown away by the talks. But I have a question for all three of you. Starting with the very first talk, it covered a lot of different domains, and you gave Steiner tree as one example of a computational model. Just curious whether there are different, each of these domains, do they require different kind of arsenal of computational models to be brought to bear? So experience from that would be something that I would like to know. And for the second panelist, you mentioned the difference between false positives, the error rates. I was just curious how you go about detecting the error rates in that. So that would be interesting. And for the third panelist, this is fascinating work, and I was a little bit disturbed to hear that this may not be accepted in conferences. So I wanted you to elaborate on that. Thank you.
So very good questions, and what I find fascinating, and actually I try to emphasize is, what we observe is there's a variety of problems that actually, occur in different settings across different applications, and you can actually get these synergies. For example, connectivity is studying connectivity. We have studied connectivity in graph theory, Steiner tree, and many other problems in network design. Well, it just happens that, there are many problems in computational sustainability that can be captured as graphs. And for example, we encounter those problems to study, to design wildlife corridors, and it's actually interesting. I'm a big believer in serendipity. In fact, a colleague who was familiar with our work concerning wildlife conservation and connectivity, by understanding how we were doing it, understood what optimization is and how computer science can provide tremendous insights. And he immediately thought, oh, this is really very similar to, placing or studying the placement of hydropower dams in the Amazon. Indeed, again, there we have these questions how the placement of dams are affecting connectivity. So you do see these themes and these cross-computational topics or even problems occur, in different domains, not just sustainability. And in fact, I think that makes it very exciting for computer science. I also gave the example of work we are doing in terms of source separation for materials discovery, where you have a signal, X-ray diffraction patterns, and you want to identify different factors or crystal structures in these images, and that problem is similar to separating elephant calls from other sounds. So you have, and we are identifying these cross-cutting computational themes, and that makes it very exciting for the students. In fact, typically, my students have these a variety of domains where they can apply methodologies, some algorithm development for materials discovery, elephant calls, etc. So I hope I addressed your question.
So just to add and maybe answer I think every kind of computational abstraction has a match in some biological or sustainability domain question. What I found both exciting and challenging in working in this domain is, and I'm a computational ecologist and have been for many years now, working with ecologists, is first of all, it takes about a year quite often to figure out how to translate the domain question into the right computational abstraction. At least, yeah. Because the second aspect of it is that we quite often we're used to having, okay, we have our solution, let's now test it against ground truth. We will not have ground truth in most of these problems, in this domain. So we have to find different ways of verifying our answer. And the third aspect of it is that our computational objectives quite often are a mismatch for the utility of the solution in the domain. And so it takes a while not only to translate the question into the right abstraction, but find the right translation back from the computational answer to the utility function in the domain. So, but in terms of which kinds of abstraction, everything. I would like to take the false positive, false negative question offline because it's pretty technical.
So there is a problem we have in our conferences. We ran this experiment inadvertently in our lab where within one office we had one postdoc doing the same problem, proving theorems, and the other postdoc going out and measuring things in the field. Guess which paper got a best paper nomination and which paper got rejected? And the review was essentially, you measured things in the field, but you didn't develop new algorithms, there's no theorems, and the paper's out. And so, unfortunately, a kind of work which is really, measuring things in the field is not easy. This requires a lot of effort. This kind of work is not appreciated, and there needs to be a space within our conferences where this kind of work is recognized. Today we smuggle it in application tracks, in data science tracks, but this is science, and this should be recognized as a primary citizen of our conferences. And there needs to be a place to do that. And if that doesn't happen, students, postdocs or not, they're not going to do this kind of work. We had a visitor from Wildlife Conservation Society all of last week. And he kept saying, you got to do more measurements, you have to do this, you have to do field tests, you have to test it on other data sets. And the PhD students are very concerned that this is not going to lead to any publications. This is, but it's really important. And why this emphasis to just keep coming up with newer models and show that it shows a little bit of improvement over the last model? Because that's how you get papers published. And this is wrong, and there needs to be a fix. And I think we need to come up with a new space to encourage this kind of work.
It's one of the reasons we have Milind here, actually. I'm just going to follow up on that before, and we'll go over there next. I strongly concur. I would just say that there's several hundred of the top AI researchers at Faculty Summit today. And so when we complain about the way that things are done, we are them, right? So, you know, there's a reason that I asked these three to be here today, because they're not the only ones, but in my mind, they're exemplars of people who have gone out and worked to change the system, put their careers and credibility on the line to say these are things that are important. I come from the other side, on the environmental science side. I've started an emerging technologies track at one of the largest ecology journals to directly start publishing computer science applications in the environmental sciences domain. Tanya's on the editorial board. Faye, who Milind mentioned, is on the editorial board. So I would just like to say that, you know, there's a problem, but if anyone's going to fix it, it's us. And also, if we take a slightly less myopic view of things from AAAI or HComp or NIPS, and you ask, how do you publish in the world's biggest journals in science and nature? That is you need strong algorithmic advances, and you need significant contributions to the science itself. So as computer science and artificial intelligence domains start looking at the bigger scientific enterprise and getting the message out in that domain. I think if you look at the recent issue of Science, was it last week or 2 weeks ago, that was dedicated towards AI. The feature article was the new scientific assistant, right? Where they're looking for AI to be applied strongly to scientific domains like environmental science and ecology.
All right, so before getting to my question, I just have to respond to this particular topic because it seems to me, as somebody who loves applications, why would you want to waste publishing an application in a conference about the theory of machine learning? I mean, take it to an environmental science conference. That's going to be the place where it's really exciting and has impact. But the question I had for you, you seem to you've taken something which sort of terrifies the civil libertarians. This is for all of you, but I think primarily for Tanya. This idea of a global surveillance society and shown the wonderful things that you can do with it. And I wonder if you have thought about turning some of that back towards asking the same questions about human populations. So finding missing people, doing real-time demographics of sort of ethnicities in different areas, studying the migrations of people from place to place. There seems to be some wonderful opportunities there if you can get around those little civil liberties issues.
Right. Right. So thank you, David. We actually get invariably asked that question. So when is the wild book for humans coming? It's called Facebook, actually. But I agree. I mean, and the surveillance for humans is orders of magnitude ahead of what we can do for animals. Facial recognition for humans is much better than what we can do for animal ID. So I would actually switch the answer. We can do already a lot of what we're doing for animals. We already can do it for humans. I'm not touching it.
And I think we have time for one more.
Hi, Barbara Gross, Harvard. First, I just want to say I too applaud what you're doing, and I'm extremely sympathetic, as Nguyen knows, to the issue of publishing. So just a few thoughts. One is, of course, as you know, anything that involves human subjects also has this problem. I will say one of the advantages that people who collect big data, like the NLP world now, is by sharing the data they have, they've made actually the collection of data important. I think, first of all, I think, Lucas, your comment about publishing in other journals is exactly right. It's a lot of work to get that data. And so there's a tendency to say, you know, do I really want to share it so other people can just do the algorithmic part? And I think what the NLP world at least has shown is that there is an advantage, and then it becomes a good thing to have collected it. So you might think about that. The bottom line, though, is I think that you're right. So, but I would urge toward thinking about open data. So I guess that was a comment more than a question, though you all can respond to that. And I know how hard it is to make data available to others. I want to say that also.
There are huge privacy concerns for example, both from Nguyen's and my work for sharing the data and privacy and security of animals. There are several wild books that we will never put online. For cheetahs in South Africa, for example, the seals one is closed. If we ever get the snow leopard one going, it's not going to be accessible because those are the data is highly valuable to poachers. So sharing data has to be done very, very carefully, you know, actually in some cases more carefully than for humans, and I'm sure for Nguyen. So sharing data is great, but we haven't figured out the right model for this domain, I think. Yeah, but we can. So I've talked about it with Ross Anderson from Cambridge University, who has done the privacy model for healthcare, and he says this is more complicated.
Okay, thank you very much. I know the Q&A session went by extremely quickly, but everybody's already milling around outside because everyone else did their jobs better and ended their sessions on time. I would just like to thank the 3 panelists and speakers today. Thank you so much. Everything you guys do is what inspires me to do a little bit more in that world every day. And thank you guys all for coming and hearing about this. And please do reach out to me about the AI for Earth program if you're interested. Thank you so much.
Thank you.